Okay, so here's another example of a double integral that we want to evaluate. This time though, keyword is evaluate, not estimate. So we're not looking for an approximation this time. We want an exact answer. I already worked this one out. Notice there's not much going on here. The function that we want to integrate, the square root of 4 minus y squared, if I set z equal to that, I would recognize this, first of all, as the equation of a semicircle centered at the origin of radius 2 in the yz plane. However, if we interpret it as a surface in 3 space, the fact that x isn't present there means x is free to vary. We've seen before that that gives us cylinders. So really, this semicircle in the yz plane can sort of be dragged along the x-axis in either direction, producing this cylinder with a semicircular base. So because the integral here represents the volume of a solid, and in this case the solid would be completely above the xy plane, so it should come out to a positive number. We can compute this any way that we can compute a volume. In this case, we have some geometry that might be useful here. So rather than try and evaluate this directly using the definition of the integral, let's just think of it as how we would calculate the volume of a semicircular cylinder like this. So notice the rectangular region R in the xy plane that we're using for our integral here. It's -4, 4, -2, 2, which would be this rectangle right here. You can see on the x-axis we're going from -4 to 4, and on the y-axis from -2 to 2, creating this rectangle down here. So drawn here is the solid that we want to find the volume of. So volume of a cylinder is, the volume of a cylinder is pretty simple. It's just the area of the base times the height. Whereas this time, the height is this little segment right here. So the area of a semicircle is 1/2 pi r squared. I've done that here. 1/2 pi r in this case is 2, so that's 2 squared. The height is the length of this interval right here from -4 to 4, which would be 8. Plug that in, we end up with 16 pi as the volume. There's not a lot of cases where we get to use geometry like this, but especially early on when we don't have a lot of other techniques available to us, you might encounter a problem or two where you can go about it this way. Okay, scroll down a little bit more. Now I had mentioned the midpoint rule for single variable calculus, which is an approximation technique for approximating definite integrals by choosing your sample points and your subintervals very carefully. So we know that from single variable calculus, if you break up that interval a, b, and select your sample points to be the midpoint of all the subintervals that you get, the approximation is supposed to be pretty good in most cases. We have a similar rule like that for double integrals, only this time we're not looking at subintervals, we're looking at subrectangles. So here, we want to use the midpoint rule where we're going to use m and n both equal to 2 to estimate this double integral right here, double integral over r of the function y squared over x plus 1 dA, where the rectangle is 0, 2, 0, 4. So as we saw before, you typically want to draw the rectangle first before you try anything else. And in my case, the rectangle comes out kind of nice. It's this rectangle right here. So my x-axis, we're using the interval 0, 2, and on my y-axis, we're using the interval 0, 4. And in both cases, we're breaking the interval up into 2 equal subintervals. So 0, 1, and 1, 2, 0, 2, and 2, 4. Okay, giving me these 4 subrectangles. Now what I want to do is choose my sample points, only this time, because we're using the midpoint rule, those sample points should be at the exact center of each of these rectangles. And it's easy enough to find the exact center because all we need to do is take the midpoint of the subintervals in our x and y axis that give us the rectangle. So the midpoint of this interval from 0 to 1 is 1/2. Midpoint from 0 to 2 would be 1. And so that's the coordinates of that point. I do that for all 4 rectangles, getting those 4 points. And then notice again, delta A the area of any one of these subintervals is 2 again, 2 by 1. That's the dimensions of any one of those subrectangles. So again, remember this summation, this double sum that we're supposed to find, we can really just think of it as adding up the volume of all 4 of these boxes that we would create using these subrectangles. But each one has the same area for its base, which is 2. So we just factor that out of the computation. And then we plug the coordinates of these 4 points into our function here. That's where I'm getting these values from. Add them up, multiply by delta A. In my case here, I end up with 320 over 15. And that's that. It's not too bad. Okay, let's go ahead and move on. Let's see. All right. So let's see, we did that. All right. So now we want to move on to a technique for evaluating these integrals where we don't need to use estimation or geometry. We want to kind of use a more general approach here. And to lead into this, we need to talk about these things called iterated integrals. Now these are not iterated integrals here. This is going to help us as a sort of a stepping stone into that concept, but these are what we call partial integrals. You're not going to hear me use that term much outside from this one short explanation, but they're essentially the same idea as a partial derivative. You have a multivariable function, f of x, y, but we integrate with respect to only one of those 2 variables. In this case, integrate with respect to x, that's what the dx indicates, or with respect to y, that's what the dy indicates. The other variable, so in this case the y, is being treated like a constant in the same way that we do for partial derivatives. So as an example here, I want to integrate the function x squared y cubed. It's a 2-variable function, but I'm only integrating with respect to x. That means I hold this y cubed constant here. If I just focus on the x squared for a second, an antiderivative for that is x cubed over 3. Y cubed doesn't really do anything. It's just there, right? It's being held constant. The interval that we're integrating over from 0 to 1 only affects the x values. Because we're integrating with respect to x, these are treated as x values, and I plug them in here. Notice when I plug the 0 in, the whole thing's going to go to 0. But if I plug in a 1, I get 1/3 y cubed. This is an important aspect of dealing with partial integration. Because I integrated with respect to x, but not with respect to y, there's still a y present in my answer. So even though this is technically a definite integral, the answer is not a constant. It's a function of y, because the y didn't get integrated out of that expression. Moving on to this example right here, you notice I get an answer of just 0. I integrated with respect to y, but there's no x present. The reason that happened in this case is if you look at the integrand, so sine of y to the 5th square root of x, if I want to integrate this function with respect to y, it's worth looking at it for a second. You may notice that sine of y to the 5th is an odd function. We talk about integrating odd functions in Calculus 1 and also in Calculus 2. The presence of this root x here is not going to affect that because we treat that like a constant. If you integrate an odd function over an interval that's symmetric about 0, so from -4 to +4 in this case, always this comes out to 0. So we don't need to do anything additional. We just kind of have a freebie in this case. Okay? So how does this apply to double integrals? Because neither of those examples we just looked at were double integrals. Well, this sort of bridges the gap for us. So in this case, let's suppose that we're dealing with a 2-variable function, f of x, y, that's non-negative, just for now. To keep things simple. The surface that we get from that in this case is this guy right here. And we want to integrate this over a rectangular region. So perform a double integral over the region AB, CD here. You can see the interval AB right here. It's this rectangle that's standing as the base of this solid. S is what I'm going to refer to as the solid, given by all the blue here. So how do we compute the volume of this thing? Well, if you go all the way back to chapter 6 in our book, pretty sure it's chapter 6, which you cover in Calculus 2, very early on in Calculus 2, you talk about calculating volumes of solids using a cross-sectional area formula. You're integrating a formula A of x, where A of x represents the area of a cross-section of that solid taken perpendicular to your x-axis. If you look at my interval here, AB, And if I were to just pick some x value within that interval AB, that's going to correspond to this cross section right here, which has its own area, a of x there. That area would be a function of x, because depending on other places where I could have chosen that x, the cross sections could look different. They could have different areas. It's a function of x. How do I compute that area? Well, if I think of the plane that's cutting through this solid to create that cross section, it's x equals some constant. That's how I would get that plane. The curve up here, which is the intersection of that plane with the surface, z equals f of x, y, is a plane curve, and you notice how it's kind of parallel to the yz plane. So I can think of it as a function of z as a function of y, giving me this curve up here. The area under that curve would be an integral, but treated as a single variable integral. So that area is given by this integral right here, f of xy dy. I'm integrating with respect to y on the interval CD. You can't see the CD here, but remember that's giving us the width of this rectangular base here. So that would be the area of that cross section is given by this integral. Not a volume, an area. Now, to get that to turn into a volume, applying the technique from chapter 6 in our book, what we want to do is integrate this area formula on the interval where we're taking our cross sections, that is the interval AB, with respect to that x there. So I'm going to take this thing, treat it as an area formula, and plug it into this integral where I integrate now with respect to x. Okay? So this would represent the volume of this solid. And one way to kind of think of this, again, this integral inside the parentheses here represents the area of this cross section, and this integral out here with respect to x, in a certain sense, you can think of it as basically stacking up all the possible cross sections and summing them, creating a volume. That's kind of a non-technical way of treating it, but it might help you to think of it in those terms. So this thing right here is what we call an iterated integral. And in the next video, we're going to talk about how we evaluate those.